My name is Warski. I come from Warsaw, Poland. Thank you very much for coming and thank you for having me at the conference. So I would like to talk about how to do dependency injection in Scala without using a framework, mainly using pure Scala and also sometimes using a library called MacWire, which I wrote. And so it's going to be mainly live coding. There's going to be a couple of slides just as an introduction, as an ending. If you have any questions, throughout the talk, let me know. If I start walking and you can't hear me, let me know. And so, so that, if you don't understand anything, I'm not clear enough this time. Okay, so let's start. So dependency injection is, in general, quite a well-known pattern, right? Especially in the Java world. If you're coming from the Java world, you probably use some form of a dependency injection container, like Spring, Juice, or Weld, or CDI. So it may seem that it's like something special, and that it's something that you need a container to actually use, right? But if you think about what's the essence of dependency injection, especially if you're using constructors to express dependencies of a service of a class, it's really just passing parameters to a constructor or to a method. So it's really nothing, it's not like some special construct, right? It is just using parameters. So the frameworks help a bit in the way that you don't need to actually write it anywhere, but each framework brings a lot of baggage and a lot of constraints. So maybe we can try to live without a framework and see how we can do it. So so that's what we are going to try and do at this talk. And a bit about me so that you know who's talking to you. I'm doing Scala for about 3 years full-time, and before that I did a bit like a hobby. I work in a company called SoftwareMill. It's a software house in Poland. We are a type-safe consulting partner. We do software for various kinds of industries, and mainly from the US, Australia, South Africa, also a bit from Europe. I personally did a couple of open source projects, like 500 Envelopes, which is an entity auditing library, and MacWire, which I'm going to talk about today, and a couple of others. I have a blog. Feel invited to visit it. Try to write about interesting things. Maybe I succeed sometimes. And I have a Twitter account, which is kind of obvious nowadays, I guess. Okay, so let's start the actual talk. So I will create a new class first. Let's call it ScalaIO, which is probably not very surprising. Okay, it will be an application so that we can run and see how it works. So when we talk about dependency injection, we need some objects and some dependencies so that we actually can inject things into, right? So we need some services which have some dependencies and so on. So such services and such objects form an object graph, right? Which we need to wire and then actually run our code. So we will need an example object graph. So we will write one down, example object graph, right? And typically these classes would be spread across packages, right? You would have one package with one piece of logic, another package with another piece of logic. Here it will be all in one. It will be only inner classes just for simplicity and for demo purposes. So spread across packages. But here we'll just write them down one after another. So we will be running a restaurant, and we want the restaurant to serve us a steak with potatoes. So we will have a couple of services which will help us do that. So we will have a field where we will grow the potatoes. We have a digger, which is used to dig out the potatoes from the field. We have a potato farm, which has two dependencies, a field and a digger. Okay. So we express dependencies using constructors. So we have the potatoes, now we need the actual steaks. So we have a cow pasture, and we have a metery, which takes a cow pasture as a dependency. And finally we have a restaurant, which has two dependencies, a potato farm and a metery. Okay? And the restaurant is going to have a single method, order steak with potatoes. and that is going to print some status that we actually invoke this method. Welcome to this. Welcome. Here's your order. Okay, so our goal is now to invoke the method order steak with potatoes on a restaurant, right? But in order to do that, we actually first need to have a restaurant instance, right? We have a restaurant instance, we need a potato farm instance, a meter instance, and so on, right? So we need to create a new instance with the right dependencies. So one way to do it would be to use a container like juice, and you would annotate these classes with add, inject, right? And so on. You would pass them on to juice, to Spring or whatever, and you would get an instance of a restaurant with all the dependencies satisfied. So it works, it's one way to do it, but there's also another way, and it's much simpler, and it's just doing things manually. Now I will do what I call manual dependency injection, and typically the wiring of the object graph is something you do at the end of the world. So when you absolutely need and have an instance of your object, you do all the wiring. So like in the entry point of the application, only when you absolutely need to, you actually do the wiring. So this will be the end of the world. Okay, so yeah, manual dependency injection, I just create the instances manually. New field, the bigger, okay. Potato farm is a new potato farm, and now I have to pass in the dependencies, right? Now the cow pasture, and the meter is similar. And it takes cows, and the restaurant is it takes a potato farm and a meter, right? Yeah. And now I can invoke the method on our instance. So just one thing before I run it, I will make these case classes so that we get nice two strings. Okay, but it's like not a requirement of doing this type of dependency injection, it's just to get two strings. Okay, now we can try running our code and seeing if it actually works. Hopefully it will compile. So yeah, so you can see that here we have the object graph printed out, right, and we have all the dependencies as we expected them to be. So nothing very surprising right now. And that's manual dependency injection. You can use it in Scala and in Java in the same way. It works pretty well. It has a couple of advantages comparing to using a container. First of all, it's type safe, so at compile time, it's checked that all the dependencies are satisfied, right? With a container, you would get an error at runtime. It's also very flexible, so you can instantiate objects like here, right? You can instantiate it using a constructor, you can instantiate it in any way. You can write any Scala code to actually create the instance of your object, right? With a container, it's a bit more complicated, and it's also faster, right? Each dependency injection container has some overhead where you need to actually read the jars that are on the class path. You need to scan them for classes which have the at-inject annotation, so there's a runtime reflection overhead. Then you have to actually create the resolve the full object graph, and so on. Here it's all done. Once it's compiled, it's a very simple Scala program. Okay, so now we will try to improve it a bit. So the first thing is that if I do something like that, so if I declare the potato farm object first and the digger second, what happens is that when I run it, I will get a null. That's because vals are evaluated top to bottom, right? So we have a null here. And so when the potato farm is created, there's no digger yet, it's null, right? So there's a very simple way to solve it in Scala, and that is by using lazy vals. So you can just make lazy vals everywhere. And when you're using lazy vals, they're evaluated on demand, right? So actually Scala will figure out the right initialization order of the dependencies, and you don't have to worry about it. So you can just run that, and you can see that we now have the dependencies initialized in the proper order. Okay? So it's like a simple rule when you are doing manual dependency injection, you just need to use lazy vals instead of vals. Okay? So that's one thing. now the second thing that we can improve is actually getting rid of writing down these new instances, right? It can be a bit tedious because you have to repeat the dependencies over here, right? So you already defined them here. Why do you need to repeat them here, right? So we can use MacWire for that. So I'm going to add the MacWire trait. And now I'm going to replace all new invocations with a wire invocation, okay? And we can get rid of the parameters. And we'll see what happens. Hopefully nothing will explode. Okay, and like that. Okay, so first let's try running that and we'll see if we get more or less the same result. Like we do, we still have the same object graph wire as before. Okay, so what happened? So wire is a macro, which means that it runs at compile time. And what it does is it generates the new instantiation code, the new instance creation code that we have seen before. So if you compare the bytecode generated by compiling that program and the one we had before with the new instance, with the new keywords, it will be exactly the same. So the compiled version is exactly the same. The only difference is at compile time. Okay? So what wire does, it takes the class as a parameter, right? And as it is invoked at compile time, it has access to a lot of information, such as the abstract syntax tree of the enclosing trait object or class. Okay? So what it does is it looks at the class, it does some compile time reflection, checking what kind of parameters are needed to instantiate that class, and then for each parameter that is needed, it tries to find an instance of that type. Okay? So here we would look at potato farm, and the potato farm is a field, right? So we are looking for a field instance. So we are looking in the enclosing trait or class object. So here we have the enclosing object, right? So we will be looking for a field instance in the ScalaIO object, and field is, right? So we will just use the field name, right? And so on. Also the superclasses are checked. So it works with inheritance. And yeah, and you know, so that code will generate your potato farm with the right dependencies, and you don't have to write it. Okay? Okay, so that's MacWire, and that's the basic idea. So how can we extend that a bit further? So the first thing is that so far we only had dependencies which are singleton scoped, right? So all of these classes, all of these instances in the scope of that application are effectively singletons, right? There's only one of them because it's a var, right? And you can check that if we add the print line here. Yeah, you can add the print line. Wait. Not first. I need to add the second dependency. So yeah. So to actually see that it is a singleton, we need to use some dependency twice. So yeah. So let's say, for example, that we have cows which eat potatoes. So we will add potato farm parameter to our cow pasture, right? So now cows require potatoes, okay? So the first thing is, when adding a new parameter, right, is that we only have to add it here. We don't need to change the wiring code because it's handled automatically by the macro, right? So when we run that, you can see that the cows have the potato farm, right? And that's convenient because if you add a new dependency, you only need to add it in one place. Okay, so now what if we wanted to have a new potato farm created for every usage? So first let's add a print line here so that we actually can see how many times potato farm is created. Potato farm, right? So obviously currently it's a var, so it's a singleton, so there's only one of this, right? So how do you make it dependent scope or no scope? The terminology varies. So that's a very simple way using Scala. You can just make it a def. If it's a def, it's invoked every time it's actually used, right? So in this time, in this case, we will get two potato farms, right? Because we have one which is used for the restaurant and one which is used for the cars. Okay? So that's a very simple way to have an object which is scoped in a dependent way, or with or without a scope. Okay, so that's I think my second step, and now let's move to modules. Okay, so as our application evolves, we are getting more and more classes, right? And our wiring code, so that piece of code over here, right? It grows larger and larger, and of course, large methods are not that nice. So if we have like 50 dependencies, that's 50 lines of code. So we may want to split it somehow, right? So what can we do? So one thing is that most probably, like, these classes are somehow grouped into packages, right? So probably that would be one package where we handle the potato growing. That would be another package where we handle the cows, and that could be a third package which handles the restaurant. Okay, and we can divide the wiring code in a similar way. So we can create modules which create parts of the object graph, and these parts are like correspond to the packages in which these classes are defined, right? So for example, we can have a crop module which defines how to wire all classes related to growing crops, right? We can have a livestock module, which handles wiring of the part of the object graph which handles cows. And we can have the restaurant module, which handles the restaurant, right? Okay. So now we can't really access the restaurant instance. We actually first need to create the application. So now that moves over here in your crop module with livestock module with restaurant module. Okay. And now our restaurant lives in the app. Okay, so these modules, they will typically live in the package next to the classes which are wired. Okay, so these modules live next to packages, and now at the end of the work, when we actually have to run the application, we simply pick the modules which we want to use, right? And then we can run an application. So there's one problem here. The problem is that this doesn't compile, which is usually a big problem. So we get a number of compilation errors. So you probably can't see it, but it says that at that line, so when trying to wire a cow pasture, cannot find a value of type potato farm, right? Because to actually create a cow pasture, you now need the potato farm, right? So, and the livestock module has no idea about potatoes. I mean, how could it, right? So we need to somehow express a dependency that the livestock module depends on the potato farm, right? And there are two ways to do it. So the first way is to simply use an abstract member. So we can say that the livestock module needs a potato farm. It doesn't say what kind of potato farm it is. It's just an abstract member, right? It has to be implemented somewhere by the application that uses it, right? But it's just a dependency of the module, right? And now when wiring, when wiring a cow pasture, the enclosing trait is going to be the livestock module, so the potato farm will be found. And later, when we actually combine the crop module with the livestock module, right? These two match, so they are used for the wiring. Now, the same problem is with the restaurant, right? The restaurant needs both the meatery and the potato farm. So we could use abstract members here as well. But another thing that we could do, which is actually also quite simple, we can simply say that the restaurant module extends the crop module and the livestock with livestock module threads, right? So that creates a very stiff dependency between the two modules, right? Because it kind of binds the restaurant module to a specific implementation of the crop module, right? So here it's like it's a very soft dependency, right? We don't really say anything about the potato farm. We just say that we need a potato farm. And here, like, we say that we want to actually use the wiring defined in that module. Okay? And now we can probably run it without errors. And yeah, we get like the same result that we actually got before. Okay? Okay, so that's our dependencies, and now, and now we can try doing something else. So let's say that we have a couple of implementations of a potato farm, right? So now we will make a potato farm trade, and that will be the traditional potato farm. Potato farm, right? So we have two implementations of potato farm, and we will also have 3D printing potato farm. Okay, so that's the modern implementation. So now we have two implementations, and we want to choose somehow which one to use. So again, we have a couple of choices here, right? One choice, which is like usually very, like it should be probably the starting choice, is we can simply include some logic here to choose which potato farm implementation to wire, right? So we can just say, for example, if config.modern, then wire the traditional potato farm, right? And else wire the modern potato farm, or the 3D printing potato farm, okay? 3D printing. So that's one thing you can do. So the config here is, of course, something you read from a file or something like that, okay? Okay, but we are not going to explore that further. It's, you know, you can just use the fact that the code to create an instance of your dependency can be arbitrary Scala code, right? You're not constrained in any way, okay? But let's say we want to approach it in a bit of a different way. So we actually want to create, we can also create two different modules, okay? So now we can say that our prop module is like a fully abstract module, and which only defines it provides a potato farm, right? And now we can say that we have a traditional prop module where we actually do the wiring as before, okay? And here we will wire the traditional potato farm, right? And it extends the prop module. And we can have a modern prop module, which here it can be a lazy file, wires the 3D printing. Okay, so why would you use that approach instead of the previous one? For example, it can be useful if the whole parts of the object graph to wire are different, right? So here, to create a potato farm, you also need to wire the field and the digger, right? And that is simply not needed in the 3D printing potato farm. So these are like completely different implementations of that module, okay? So now, of course, so now we have a crop module, which is like an abstract module, and we have two more concrete implementations, which provide specific implementations for the potato farm. So now, of course, when we create the application, we have to specify which crop module to use. So we can specify the traditional crop module, right? So that will be one application. Let's call it crop one. And we can create another application, which will have like a completely separate object graph, right? Because it doesn't share anything with the modern crop module. Okay? And let's try running that. And maybe we'll get lucky. And we did. Okay. So that's the output of the first application, right? It uses the traditional potato farm with the field and the digger, right? And here we have output of the second application, which uses this 3D printing potato farm, right? And you know, we just swapped the trait here, right? The implementation of the crop module. And also an important thing to note is that all of the other dependencies like the restaurant, right, which is a lazy bar, so it is a singleton. However, the restaurant over here and the restaurant over here are different. So they are singletons in the scope of the up1 or up2, right? Because there are lazy bars in that wiring, in that object graph. Okay, so that's how you can create multiple implementations. And for the final example, let's look at some other features that EDI containers sometimes provide. So I just removed the second application for clarity. And let's look at interceptors and AOP. Interceptors and AOP are a very useful thing. They let you sometimes express logic in a concise way. So how can we do it with like minimal overhead and using as much Scala as possible? So first thing, let's say we want to intercept all calls to a restaurant and we want to surround it with a transactional interceptor, all methods, right? So the first thing is we have to define that we need a transactional interceptor. Okay. Transactional, yeah, this is right. Okay. So we have defined an abstract interceptor, so we just declare that we need an interceptor which is called transaction, right? We don't say anything about the actual behavior of the interceptor, well, except the name that kind of gives away what it's supposed to do. So now we have an abstract interceptor. Interceptor is a very simple trait from MacWire. It defines only one method, apply, and it takes an object of type T and returns an object of type T. Right? So the idea, of course, is that it takes an object where the methods should be intercepted and returns an object where the methods are intercepted. Right? So let's use our transactional interceptor. So we can say we can use it like that. So now we say that the wired restaurant object should be surrounded by the transactional interceptor. Okay? Now, at some point, of course, we need to actually implement the interceptor, right? So, a good place could be, for example, when we actually do the wiring. So we can say that the transactional interceptor is a proxying interceptor. The proxying interceptor is a very simple class from MacWire. It's like maybe 20 lines of code, which implements an interceptor through JavaScript proxies. So for a proxying interceptor, we need to provide the behavior of the interceptor. So we need to provide a closure, which takes the context, which is the invocation context. If you have ever written a Java interceptor, it will be quite familiar. It contains the method, the parameters, the intercepted object, and so on. So we can now. I always in my notes. Now we can actually. So we won't implement transactions. We'll just see that it works. About to invoke restaurant, and now we get the result. And now we just write that it's invoked, restaurant invoked. Okay, and we return the result. Okay, so let's try running that. So the proceed method actually invokes the method that is intercepted, and you can see that we get kind of what we expected, right? We get the first method, then the method is invoked, which does the print time, and then we get the result. So in the end, we get like a very simple interceptor implementations. It's quite declarative. Here, it's very similar to annotating the restaurant class with an annotation, right? Except that we use pure Scala. We don't need any containers to actually do any scanning and so on. And also, what it allows you to do is it allows you to actually test that interceptors have been used, right? It's not something you could easily do in a normal Java setting, for example. So let's say we have an instance of our application for testing, right? So here we are at liberty to provide any kind of implementation of the interceptor that we want. For example, we can use a no-op interceptor, which doesn't do anything, right? So let's say that for testing we want to turn off all logging, or we want to add some extra logging, or we want to remove transactions, or we want to actually write an interceptor which checks that it was invoked, which can be important, right? It can be a business requirement that the interceptor is actually used in some places, right? So you can't easily do it with a container. Here you can just write code which checks if it was invoked, right? Okay, so while we are testing, another nice thing is that you can quite easily do integration testing. You can easily test each of these classes. You can write unit tests, right? Just providing mock dependencies as you would do ever. But here you can also test the whole object graph or the parts of the object graph by instantiating the modules and providing the dependencies, right? And also in a very easy way we can provide mock dependencies, we can provide mock implementations for some of the dependencies. So we can simply override, let's say, I want to override the potato farm, what the field, let's say. And I just want to provide some mock implementation of the field, right? So let's say it's a mock, right? That's a new object, it doesn't matter. So, and if I now run this code, it doesn't, you can't see it really. So the potato farm would be better. Because it has some dependencies, potato farm and new potato farm. Okay? Now it won't compile. Yeah, of course it doesn't, because we have to say here that it's actually a potato farm so that we can override it. Okay, so now here, because it's an anonymous implementation of a trait, you can see that the dependency, right, is a very ugly name, but you can see that it's different from what we have seen before, right? And just by overriding some dependencies, we can, and it's probably used twice. Yeah, here's the second place, right? And we have just provided a mock implementation for just one class from the object graph, and the whole rest of the object graph is wired as always, using our mock dependencies. Okay, so we still have some time, so I just want to quickly show you how we can use it in play. So normally in play, play is great. However, one thing I don't like is that you have to create controllers as objects. So actually you don't have to, it's just the default way. So how can we use manual dependency injection or MacWire to improve it? So here I have an example in play. It's exactly the same example that we have seen before, except that the classes are in separate files and they have their dedicated packages, right? So we have the crop package, where we have the digger and the field and the potato farm classes. We have the module in the package, which defines the wiring for that part of the object graph. We also have controllers, which are normal classes, and which have some dependencies, like here, okay? And so we need to have, they use the dependencies to, render some HTML and so on. So, how to make it work with play? So first of all, we need to have some place where you actually create the whole object graph, right? So let's just create an application object, which extends the modules that we have defined, and also does the wiring for the controllers, right? So now we have the controller instances inside the application object. So the integration point that we have to provide is we have to implement the getController instance in the global object. So that's something that Play recognizes. And the getController instance is pretty self-explanatory. It gives you an instance of a class giving the class, right? And MacWire has some helper methods for actually generating a map which goes from a class to the implementation, and it also respects the subtyping. The final thing that you have to do is in your roots, you have to add the add sign if the controller isn't an object, but if it's a class, then it should be dynamically looked up. So you can just check it works, as you run, and at some point it should actually start. Okay, so we're started. Localhost 1000. And yeah, and you can see that it's more or less the same as we have seen before, right? We have our restaurant object graph. We can just like method edit to harvest the field, and you can see that it is actually a single topic of the same field here and the same field here. Okay, so that's how we integrate the plane. And now just for the end, I have a couple more slides. Now what's the order? n-3 would be first, right? It's a very complicated way of naming your slide. If you are interested in doing dependency injection only with Scala, there's also something called the cake pattern. So it actually, the modules that you have seen, it is like part of the cake pattern. That's why I call it the thin cake pattern. The cake pattern moves the implementation inside the trace as well. I'm not a big fan because it creates quite a lot of boilerplate, but there are some good sides as well. Like you can more easily use abstract types. So if you're interested, take a look. Just to sum up MacWire, the basic idea in MacWire is to help you create wiring code for class instantiation. It's like an add-on. You can just do manual dependency injection without MacWire, and it works very well as well. In MacWire, you also get some other things, such as the interceptors I have shown you, generating the lookup map. There's also very similar interceptors. You can implement request and session scopes with very minimal glue code in your web framework. Okay, so that's almost everything. The source for the presentation that you have seen is over here. There's also a link to a guide, explaining step by step more or less what we have from here, except that the biggest difference, I guess, is that it doesn't use a restaurant, it uses trains as an example. The MacWire project is open source, it's Apache 2, so you're encouraged to fork, take a look, use it, contribute, and so on. And finally, I have three things. I have two kinds of stickers. So one sticker says I'm part of my code, and it's like the motto of our code review tool, which we have written in our company and we use ourselves. And we want to see if others find it useful as well. So if you'd like an I'm part of my code sticker, come and see me. I will put them out here. So the second thing is Scala times. If you're interested in Scala, and chances are you are, since you are here, we have a weekly Scala newsletter, which contains a bunch of interesting Scala links each week. I also have some, probably maybe you can see over here, this is Scala times sticker. And finally, we will have a free to attend Scala conference. So it's in April, so it's like the perfect complement to ScalaIO. Right? The ScalaIO is in autumn, Scala is in the spring. It's in Warsaw, Poland, so I invite you to visit. It's as I said, it's free to attend, though you have to come, of course. And yeah, so if you'd like to ask me about that, please do. And now maybe we have some questions. Yeah.
Would MacWire work if the modules are in different computation units in different jars?
So the question is, would MacWire work with the modules and different computational units? And the answer is yes, because in the macro, if it's in the same computational unit, you get an AST and you can inspect a lot. If it's not in the same computational unit, you get a symbol, but still it is possible to inspect what's inside there. So what are the types defined? So yes, it will work. Yeah?
You mentioned that the wiring, is it the first instance scope, the last one, or before when it's looking for this?
So are you asking if there are multiple implementations of a single type?
Rather, like when you wire, it's the first, let's say there's just one element of a given type, so how does the macro work? It's looking for the first instance of that type.
Okay, so the question is, if I understand correctly, does MacWire use the first implementation found of a given type? And the answer is no. It tries to find all implementations of a given type. And if there's more than one, it throws an error, and you have to manually resolve it. So it would be quite dangerous to actually take it first, because it may be surprising. Yeah?
I guess if you have strings in your constructors, or things like that, you have to wrap them in classes or threads. Because if you have a...
You need to have some distinct type. Yes. Yes. Sure. And though you can simply create like small marker traits which differentiate, and you can always fall back to just writing it by hand, which usually works forever.
And will it support value classes?
Sorry?
And will it support value classes for this? Like wrapping a string?
Oh yes, sure. Like if it's a it doesn't care what it is. It can be, so it supports like function types, because it's a compile time, it also supports generics in a very nice way, because the generics are not erased at compile, right? So it does like full subtype checking the way Scala does it. Okay then, so I will be here for the rest of the day, and I invite you to come ask me questions, take some stickers, and thank you very much.